This is the fourth lecture in the first semester Java course presented by Savage River Research. To view all the currently available lectures, point your browser to savageriverresearch.com and click on Open Courses. This lecture assumes that you completed lectures 1, 2, and 3 and are prepared to proceed with lecture 4. But before we begin with lecture 4, let's review the solution to the programming problem assigned at the end of lecture 3. Your client wants you to write code that will place this line from the works of Omar Khayyam on the screen. So, program 3 requires you to produce this output, just as shown. And that's where you should start. Just fill in the println statements, test it, and proof it. Does your output match the client's requirements? If not, debug and correct. Don't write junk. In the real world, it will get you fired. Get in the habit of making things work correctly. Okay, let's start on lecture 4. Internally, individual characters, like everything else in a computer, are stored as binary values. The only thing the physical computer does is manipulate zeros and ones. Character data in Java is stored in the Unicode format. As of September 2021, there was a repertoire of over 143,000 characters in the latest version of Unicode, Unicode 13.0. The set covers 154 modern and historic scripts, multiple symbol sets like the math set, and the formatting characters required to display different languages correctly. Text written in English and most European languages is read in descending rows, reading from left to right on each row. Hebrew and Arabic read from right to left. Chinese in descending columns rather than rows, reading down each column, moving column by column from left to right. Now, we didn't always have that enormous character set. The internet is a product of DARPA, the U.S. Defense Department's Advanced Research and Projects Administration. The first character set was ASCII, the American Standard Code for Information Interchange, and these same values are carried forward into Unicode. When machines communicate, they establish whether the information should be interpreted as 2-byte or 4-byte chunks. The most common setting is 2 bytes, which covers the majority of modern languages and their formatting requirements. And that's how Java stores text by default. So the characters capital A and B would be stored as zeros and ones in 2 16-bit sequences like this. When you're looking at the ASCII chart, it only shows the lower 8 bits for each of the characters because the upper 8 bits are always 0 for the basic ASCII character set. Those binary numbers represent the decimal values 65 and 66 respectively, which Java will print as the characters capital A, capital B. So that should complete the discussion of the 8 primitive data types from lecture 3. And previously we covered the 4 structural reserved words, class, public, static, and void, in lecture 1. Now let's move to the primary topics of lecture 4, beginning with arithmetic operators. There are 5 arithmetic operators: addition, subtraction, multiplication, division, and modulus. These operators are called binary operators because they must have 2 operands, a left, highlighted in red, and a right, highlighted in blue, as shown in the right column under examples. The arithmetic operators work as we would expect, and as usual, it's an error to try to divide any number by 0. So consider the following code. Z is initialized to 1 on line 8. And on line 10, when I divide y by z minus 1, I'm dividing y by 0. So why don't I have an error? Why don't I have that red icon in the left margin of line 10? What's going to happen when I run it? Well, I don't know either. So let's run it. The JRE, the Java Runtime Environment, choked at line 10. This is a runtime error. That's the terminology, runtime error. Prior to this, we've only seen compile time errors. Those are the easy ones. For a compile time error, Eclipse is going to show you right where the error is and give you a smart pop-up to help you understand it. But neither the Eclipse compiler nor any other IDE I've used is going to catch this. And of course, runtime errors are a disaster waiting to happen, a programmer's nightmare. Consider what happens in the real world where you're generally trying to write programs for large, dynamic, very complex problem domains. Code that can run over 1 million lines. You cannot exhaustively test a program of that size because there are too many possible paths of execution. It would take years, in some cases millennia, to run such a test on a mammoth code base. Even in commercial-grade system-critical software, the testing that's done only covers a fraction of the set of possible paths of execution. So you're the one that has to guarantee that there's no possible set of inputs that would result in division by 0 anywhere in the program. Now, when you're testing to try to catch runtime errors, and you get one, Eclipse will show you exactly where it is. Use your mouse to move the cursor to this line. As soon as your cursor is on it, you get the pointing finger. That's Eclipse's indication of a hyperlink. As soon as I click on it, Eclipse takes me right to the line where the runtime error occurred. And it really doesn't make any difference if I make the division by 0 explicit. The compiler still isn't going to catch it. It isn't going to show up until the program runs, then burns and crashes. But division requires close attention for another but related reason. In a Java program, what's the value of x after this line is executed? Take a minute. Pause your video. Think about it. What will be the value of x after this line is executed? The answer is 0. Integer division will truncate any decimal remainder. Integer division on a fractional expression can subtly introduce a 0. Now, in many problem domains, and almost all scientific and engineering domains, mathematical expressions can be very complex. And there is a set order in which arithmetic operations will be carried out. These are the 5 common operators: multiplication, division, modulus, highlighted in blue, and addition and subtraction, highlighted in red. But in evaluating mathematical expressions, Java adds a 6th category, unary negation, as the highest priority. Unary negation simply negates the value of the operand to its right, but it has no operand to its left. Now, the 2 -4s highlighted by the purple arrows are unary negation. Neither one has an operand to its left. But this is not unary negation. This minus sign has an operand to its left. Unary negation is not a binary operator. If a minus operator has an operand to its left, it's just simple subtraction. Multiplication, division, and modulus are binary operators, as are addition and subtraction. All five only work with two operands. But in an expression like this, the question is, in what order are these operations performed? If I subtract 6 from 4 first, I get minus 2. Then when I multiply by 3, the result is minus 6. But if I multiply 6 by 3 first, I get minus 18. Then when I subtract that from 4, the result is minus 14. The Java compiler, like the compilers for C, C++, and C#, will evaluate all of these expressions in a series of passes. So let's look at how that works in more complex expressions, and we'll look at this one first. To evaluate an expression, the compiler makes 3 passes. The first pass looks for unary negation, a minus operator that has no operand to its left. The first pass will be from right to left, looking for a minus operator that has no operand to its left. There's only one, here. So the compiler converts the 4 to a negative 4. That's the end of the first pass. The second pass is from left to right, looking for multiplication, division, or modulus. And in that second pass, the compiler would find the modulus operator here and evaluate. Remember that the modulus operator simply produces the remainder of integer division. Having calculated that, the compiler moves right and finds multiplication and evaluates. Then the second pass will continue moving right, but it will find no additional multiplication, division, or modulus operators. So now we move to the third pass. On the third pass, we're moving again left to right, but now we're looking for addition or subtraction. And here's the first one. The unary 4 simply made 4 a negative number, and we did that on the first pass. So the compiler evaluates, producing this result. Moving again to the right, the compiler finds a plus symbol and evaluates, producing the result 11. Okay, let's tackle the last one. Start with the first pass. Moving from right to left, searching for a minus sign with only a single operand on its right, no operand on its left. The first pass produces no unary negations. Now the second pass. Moving left to right, looking for multiplication, division, or modulus, and it finds 3 divided by 4. But integer division with a result less than 1 is evaluated as 0. Now, moving right again, the compiler finds 6 times 3. Now, notice that this is not a minus 6. This is not unary negation. This minus operator has operands to its left and right. So the compiler is evaluating 6 times 3, which evaluates to 18. And that's it for the second pass. So on to the third pass. Moving from left to right, looking for addition or subtraction. 6 plus 0 evaluates to 6. Then 6 minus 18 evaluates to minus 12. Of course, the obvious question is, if I code this on Eclipse, will I get these results? Well, that's a fair question, and I'm glad you asked. Here's the code for expressions in X, Y, and Z, exactly as they appear in the slides. And here are the results. And again, they agree with the hand-coded examples. But I know you have another question. Does the compiler require that the minus sign be attached directly to the operand to trigger unary negation? That beats me, so let's code it with a space between the minus sign and the 4 and test it. I love it when the magic works. But I know you have one more question. You were just about to ask me, what'll happen if I just jam it all together? No spaces anywhere. Will the compiler choke? Apparently not. Produce the same result. 3-pass compilation of mathematical expressions based on these orders of priority and associativity is foolproof. Modern compilers parse everything you code, not just mathematical expressions, but also the complex structural expressions, loops and if-else statements and methods and complex Boolean tests. All of these use analogous algorithms to produce consistent, reliable results. Okay, now let me ask you a question. Can you parse this to produce the correct result? Pause your video and write down your answer before you restart. Go ahead, pause it. Nobody's watching. Every semester that I taught this live, I had at least one student who could rip through this one, and far worse, and consistently nail them all. But for the rest of us, me included, it's unreadable unless you start working it through, starting with the first pass to find any unary negation. And here we can see that we have to make 17 a negative value, then continue with the second pass, moving left to right, and I'll be inserting parentheses to encapsulate multiplication, division, and modulus operators as I find them. And the first one you would encounter is 4 mod 3. Then that result is multiplied by 13. Then 8 divided by 6. Then 12 multiplied by 4. Then 6 multiplied by 3. Now, the compiler would have been evaluating these expressions as it found them. But I'll do the evaluations now. 4 mod 3 is 1. 1 multiplied by 13 is 13. Integer division of 8 by 6 is 1. 12 divided by 4 is 3. And 6 multiplied by 3 is 18. Now finish with the third pass, doing addition and subtraction, moving left to right. And the result is minus 18. So my advice in evaluating an expression like this is to use parentheses. Of course, you may wish to confirm your work by comparative coding, but parentheses can also be coded into the expression, and when they are, they also have their own set of rules, particularly when there are multiple sets and some of those sets are nested. And the first rule is that parentheses have the highest priority. And when they are used in an expression, the compiler is actually making multiple nested passes to locate the innermost parentheses. Consider this expression. On the first pass, the compiler finds the two innermost sets and evaluates them by the rules we just discussed. The next pass evaluates the contents of the external set of parentheses by the same three rules. Once the contents of all sets of parentheses have been evaluated, all that remains is to evaluate the remaining expression. Okay, that's it for arithmetic operators and parsing mathematical expressions. In the next lecture, Lecture 5, we'll look at concatenation and Oracle's Java documentation.